Hello and welcome back to the channel. My name is David Young and I'm a computer science student at Concordia University, Chicago. Today I'll be kicking off my software engineering basics series with an introduction to software engineering. What is it? And what does it look like? How do we talk about software engineering? And then throughout the rest of this series, we're going to talk about some of the specifics and get into what does software engineering look like in practice. So in our next episode, we'll talk about software engineering versus software programming. You may hear these terms used interchangeably, but there's actually a big difference, and we're going to address that. In the video after that, software processes and methodologies, we're going to talk about how is the software engineering actually implemented? How do we take the principles of software engineering and put them into practice? Then we'll talk about real-world software costs. Where are the pain points for budgets in software engineering? What does it look like to finance a software engineering project? And how can we cut some of those costs? And then finally, we'll talk about challenges and professional issues of software engineering. Software engineers have a lot of responsibility, and we'll talk about how to navigate that responsibility and address some of the common challenges that are uniquely arising in software engineering. But first, let's talk about what is software engineering. Well, we can talk first about what engineering is. Engineering is the application of scientific principles and methods to the construction of useful structures and machines. An example of engineering would be civil engineering, where the principles of physics and mathematics are used to build things like bridges and buildings that are useful for society, for instance, to get your car from point A to point B. Well, software engineering is just the application of the principles of computer science, our knowledge of how computers work and our programming languages to build applications that are going to provide value to users and to companies. Parnas defined software engineering as the multi-person construction of multi-version software. And so we'll see that software engineering is a team sport. It's not a solo endeavor. Software engineering, therefore, requires not just strong knowledge of code, but also teamwork, communication, and other soft skills, as well as strong organizational principles. Software engineering problems are also very complex. That's alluded to partly in the definition of multi-version software. Software engineering isn't done when the product is delivered to the customer. Software engineering is an ongoing process of revision, of problem solving, of maintenance, and of addressing arising customer needs. And so we'll see that software engineering has a unique complexity to it. As we alluded to earlier, software engineering is not just about the raw skills of programming. There's also a lot of other stages of software engineering that are outside of the coding process. You start by needing to gather clear, specific requirements from a customer in order to develop the product that they're envisioning and that is going to meet their standards. Then you go to a design. Before you actually write any code, you need to plan out your project so that you can ensure that everything works together well. Then you actually do prototyping and you put some code into the system to make sure that it works. As you go throughout that process, you're going to be testing that product so that you can make sure that it's functioning as it's supposed to. And then finally, iteration. You're not going to leave the product as it is when you deliver to the customer, but you're going to be continuously improving that product and addressing any problems that are going to arise with that. Software engineering studies how we can make all of these processes, from requirements to iteration, better and more efficient. Software engineering also functions under constraints. So for instance, software programs are going to be constrained by the hardware that they're meant to be run on. So software engineers have to keep in mind how their program is functioning, its efficiency, and whether or not it's going to actually work for customers on their system. Additionally, the safety of software, you can think about self-driving car algorithms, for instance. It is absolutely crucial that they get those right. And so software engineering takes on an additional gravity, and it functions under the constraint that it needs to keep people safe and obey the laws of the road, for instance. Reliability, software needs to be up. It needs to be functioning most of the time, and particularly essential pieces of software need to be reliable. Security, software engineers need to work under the assumption that hackers are going to be trying to break into their software. And so that changes some of the principles and practices that are undergone by software engineers. Time, budget, and ethics are also constraints. The project can't take indefinitely long, and it can't cost an indefinite amount. So all of these are things that software engineers are going to have to consider when they're developing their products. The goal is to deliver software on time, on budget, and to user specification. Software engineers, as we alluded to earlier, face ever-present difficulties that some of which are very unique to the software engineering field. We talked about the particular complexity of software engineering projects, but also there's a certain particularity to software engineering. No two projects are the same. Everyone is different, and so it's hard to universalize principles for software projects from start to finish when every project looks a little bit different. Moreover, software itself is very difficult to conceptualize and to think about. You might understand the software that you write, but it's going to be a challenge to communicate that to another person. And moreover, it's hard to get a grip on exactly what's going on in the machine. And so it's going to be important for software engineers to have models and ways to understand how software is functioning. Software is also reliant, and so if hardware goes down, so does software. And so there are a lot of contingencies in software engineering that are going to need to be considered and addressed by software engineers. And finally, software engineering is not just about the raw knowledge of code and how to program. There's also a managerial, psychological, and social component. How are you going to get your team to work together to deliver this product and to deliver it in the most efficient way possible? Software engineering addresses these concerns. We'll take a brief look at the history of software engineering. About the 1960s, computer programmers aren't undertaking vastly complex projects. As a society, we're beginning to understand how computers work and how we can use them. And so what's going on is that programmers at this time were translating existing solutions into machine instructions. An example that Coe gives is the quadratic formula. We already know how that works, and so to translate that into machine instructions is a relatively simple task. It might take one or two people, but it's not going to have the complexity of modern software engineering. But by the late 1960s, big commercial software projects are getting off the ground. And so what's happening is that these companies are realizing that having a bunch of engineers working relatively separately is not the best way to develop software, and there are some inefficiencies that are happening. And so in 1968, the first NATO Software Engineering Conference was convened in Garmisch, Germany, and it was attempting to solve problems in software engineering projects at the time. For example, projects that were coming in late and that were spending way more than the budget, and that weren't ultimately working very well. In 1969, they followed up with a second conference in Rome, and the principles established at these two conferences are still really important for software engineering today, and sort of set the groundwork for the birth of software engineering. Well, why is software engineering relevant today? Well, for one, software is everywhere, and all developed nations rely economically on software. Moreover, spending on software engineering dominates a large portion of the gross national product for all developed nations, and so there's a huge market there, and it's crucial to the economies of these nations. And also, software-based systems are ubiquitous. Think about your cell phone. Now, software is a part of your car and electronic banking, hospital systems. And so, when these pieces of software fail, it's more visible, more expensive, and more dangerous than ever. Because so many crucial systems rely on software, it has to be really good. And so, software engineering is going to give us some theories and methods and tools to make sure that our software is meeting our needs and protecting people rather than failing and leaving them high and dry. Software is more complex and crucial than ever before. Software engineering disciplines the production of software to meet constraints while producing high quality, reliable products. This is why we embrace and embark on software engineering, so that we can have this discipline and this method to tackle these hugely complex and hugely important projects in a way that's going to be more systematic and more careful and is ultimately going to lead to better software. Thank you so much for watching this video. In the next episode, we're going to tackle the difference between software engineering and software programming. If you have any questions about this video, please leave them in the comments. And don't forget to like, share, and subscribe this video so that more people can learn about the basics of software engineering. Thank you, and see you in the next video.